Good day, everybody. We're looking at an expression that would be quartic if you did it kind of the typical way. It would be fourth degree. We're trying to find the product of the roots of this expression. What makes it kind of nasty is this is a radical. So if you bring this other side and square it, it goes away nicely, but then you would have a fourth degree equation, and that's called a quartic, right? And we all know that that's a real pain to solve typically. They can be rigged to where they're easy to solve, but in general, if you just randomly pick coefficients, you're not going to be able to figure it out, Okay, so this is quartic in character if you proceed the normal way. But notice that this expression is 20 less than the radicand. And we use that very effectively down here. We're going to go ahead and just let rho equal to this piece right here, and then observe that our expression becomes equivalent to this much simpler expression. Okay? And again, just we got to remember this. We'll have to come back to this assignment, but the processing now is quite a bit easier. Now notice if you take the radicand to the right-hand side and square, and then bring it back, you get this expression. I didn't show that step. Now this equation over here contains any solution that might be in a solution to this equation. That's important. It contains, but it may contain more. Those are sometimes called extraneous solutions. Okay, so let's see how this goes. Now, this admits a very nice factorization here. We have rho minus 5 times rho plus 4. When you perform this, they call it, irritatingly call it foiling. First, outer, inner, last. It's a bad thing though. Okay, so we got this. It's an acronym you have to memorize when it's just really a double application of the distributive property. Okay, and teachers have taught it that way forever. They don't realize what a mistake they're making sometimes. But we get P equals 5 and also negative 4. Now, to the trained eye here, you typically think, well, this is going to be extraneous. Not always, I think, but if you put 5 in, it works, right? So 5 definitely checks. But if you substitute negative 4 right here, you would get negative 4 minus 4, right? Because this would be 16 here. And so 5 is the only solution. Negative 4 would be extraneous in this context, okay? It is a solution to this equation. But now remember what we did with our assignment here. This means that rho is equal to 5, but we assigned rho to the left-hand side. So notice that if we set this equal to 5, that intimates that x squared plus 31x, if you subtract 5 from this side right here, you get 24 equals to 0. So we have a quadratic, and y'all, something quite similar. You may think, well, what about this part? Well, the same thing will happen, because remember, this is just rho plus 20, so it all works out the same. And so we end up getting this equation, and this equation is equivalent to this equation. Remember, we got rid of the extraneous character of this thing with not even considering negative 4, right? So that's kind of sweet. If you hadn't have done the substitution, you'd have been stuck in a difficult trap. You would have a full-blood, bona fide quartic equation, and you wouldn't be able to solve it. You couldn't solve it. You'd have to use technology, and then where's the fun in that, right? Okay. But notice that we have some more good luck here. If A and B are the zeros, and this is super well known, although it's not taught that much in a typical U.S. high school. It's very well known in Europe and in many other countries, but for whatever reasons, in the U.S., they may tell you that the special case quartic, or quadratic, but then they just don't cover Viettas in that much depth. Okay, but notice that this is equal to x squared minus a plus b. In defense of the teachers, they have so many other things to cover. The Viettas is sort of an exotic topic, and so they need to make sure that people understand the basics. So there's no disrespect to the teachers, but I know it's emphasized a lot more in other countries and not so much in the U.S. Now, so you have this, but you see what we get here. That this is the product of the roots, right? This AB is the product of the roots, and that's what we're trying to find. So our AB is equal to 24. Okay, which is right there. There it is. That you just identify it. You compare the coefficients. Okay, so the product of the roots is 24, which is the solution to the problem. And I thought super interesting problem, folks. Now, if you work this out, I think you get a cubic. I'm not sure if you get a cubic with two complex solutions and one nasty irrational solution. And you know how it is with complex conjugates; they multiply out and just give you a number, because of I. The product of a complex number and its conjugate is always guaranteed to be a real number, and so that's how this is even possible. That we have no idea what the values of the roots are. One of them maybe is, I don't know if one of them would be, I'm not quite sure, but I know that 24 is correct, and you can check this if you want to drudge through this the hard way, so to speak, or use technology to verify, but it's weird to think that this could be the answer to this, just 24 out in the, where did that come from, but it's correct. All the steps here are correct, and this seems almost like you're cheating to take a nasty looking problem like this and actually get the product of the roots in such a straightforward fashion. All right, that's all. Thanks for reviewing.